Hello there, exercise 17A today. We're going to look at some probability, our first look on probability. Now, I'd consider this to be part of statistics, so it comes up in the exam. Basically, we end up with three papers we have to do. Paper 1 is what I'd consider to be called pure, or sometimes called pure core. Now, this is like algebra. All the algebraic stuff we've been doing will appear on this paper. Now, paper 2 has also got pure core on it, but it's also got statistics, so stats on it. And paper 3 has also got pure core, but this has something we'd call mechanics. And so you can see that the basic premise of the exam is that there's lots of algebra. The algebra appears on all three papers. But then on 2 of the papers you either get statistics or mechanics. And at the moment we are doing the statistics part of this paper. So just bear that in mind. It appears on paper 2 in a year and a bit's time. But anyway, so we're looking at some probability. And I suppose most of this should be fairly straightforward from GCSE. A quick starter. 2 dice are rolled and the sum, we should know this means the total. The sum of the numbers on the uppermost faces are added. So by that they mean when I roll the die, the number on the top. It's a posh way of saying what number it is. What's the probability of getting the 7? Now pause the video and see if you can write down what that is. Look, I'm hoping now that you've done that then. Now look, the easiest way to see this, I think, is to draw what we call a sample space diagram. And the sample space diagram is where you list the outcomes of the first die, and obviously that's 1 to 6, and you list the outcomes of the second die, and that's also 1 to 6, and you say, well, I've got to add these together. So this sample space diagram says you could get 2, 3, and there's obviously a pattern in all these numbers, and basically that 7 comes from 1 and 6, or if I've got a 2 and a 1, that's 3, 4, 5, 6, 7, 8, and again this 7 is what I'm after. That's how many ways I can get 7. Obviously a 2 and a 5 is an alternative. If I keep going on this, now you could just do this in your head and suss how many there are. The more times you do this, the quicker you and the less work you have to do, because you kind of know what's going to come up. You know the structure of this. But you can see there's lots and lots of ways. Like 10 there, I get with a 4 and a 6. But interestingly, a 6 and a 4 will also give me 10. They're different ways of doing it. How many 7s? 1, 2, 3, 4, 5, 6. Out of how many different ways? And if you count those up, there are 36 numbers. And it just so happens that simplifies to 1 out of 6. So the probability of getting a 7 when you roll 2 dice is 1 out of 6. 1, 2, 3, 4, 5, 6 ways out of the 36, which simplifies to that. Hopefully you got that right. 1 out of 6, there it is. Notice the notation, by the way, probability, and then the thing that we're talking about in brackets. Probability of getting a 7 is 1 out of 6. Basic probability then, again, another look at this. It's looking at sample space diagrams again. It says a die is rolled and a spinner is spun. Now obviously the spinner goes from 1, 2, 3, 4 by the looks of it, and it's a normal die. The 2 numbers are added together. Draw a sample space diagram. Oh, right, I'll draw a sample space diagram. Let's do the spinner first. What are we doing with these to get a score added together? So we just check on that. You don't want to do the wrong thing. Let's do the die going across. 1, 2, 3, 4, 5, 6. And the spinner going down. 1, 2, 3, 4. I'm adding them together. So I get 2, 3, 4, 5, 6, 7. In fact, it's very similar to what we just did, apart from I've got less rows going down because the spinner only goes up to 4. So this is my last row. So what's it say? Find the probability of getting the score of 9. Okay, well, it just seems to be 2 9s. So that sounds to be 2 out of 4 times by 6 is 24. So 2 out of 24, which is obviously a 12. What's the answers? A 12, there you go. Mutually exclusive events. These are 2 rules, again, that you should have seen at GCSE. And I'm also talking about independent events here by the looks of it. The 2 rules are basically this. and I shall use proper English if you prefer. Now, probability of A happening or B happening. At GCSE, we learned that if the probability of two events happening, well, you can just go probability of A plus the probability of B. Notice the posh notation for this. This is like set notation, and this symbol here means or, and you will see this. So that's why I'm showing you it. Notice this rule is actually true for mutually exclusive events. So that only works as long as the two events can't both happen at the same time. So if it was a question about sun and rain, what probability of it being sunny is, I don't know, 0.7 tomorrow. But there's a probability of it rains as well. Now, probability of rain might be 0.4. Now, notice it could be sunny and rainy at the same time. You do get days like that. You get big old rainbows in the sky. When that happens, obviously, they happen at the same time, and therefore they're not technically mutually exclusive events. So these, the rule doesn't work for these, because this rule only works for mutually exclusive events. It's a posh way of saying the two events can't both happen at the same time. Make sure you write that down if you didn't understand it before. The kind of events you can do this for, though, is I roll a die, and I can get an odd number, for instance. And I roll a die. Well, we should know, by the way, on the normal die, that's a half chance of getting an odd number. And I might also say the probability of getting a 4. Probability of getting a 4 is a 6th. Now, what's the probability of getting odd or 4? Well, these you can't both be an odd number and 4, so you can add these together. A half plus a sixth is 4/6 or 2/3. You can simply add these together. So you'd be aware of that. Second rule, also seen at GCSE, probability of A and B. You saw this quite a lot when you drew tree diagrams, if you remember. And when you have two events, as long as they're independent events, now that basically means one event doesn't affect the other. So the probability of A times by the probability is what we do. Again, notice this symbol here. This is set notation, and it means and. And I always look at that and I think, it looks like an N. And so the one that looks like an N is the and, because it's got an N in it. The or doesn't quite work quite as nicely, but it's the other one. It looks like a U shape. But it means technically the union of. This one technically means the intersection of. That comes back to Venn diagrams, if you remember that. And this tells you can multiply. There's an additional formula, though, not from GCSE, which we can use for non-mutually exclusive events. I did say this is mutually exclusive. What happens if they're not mutually exclusive? Well, here it is. Notice, probability of A or B is you can add them together. Yes, you can, but you have to then take away, well, a posh name is the intersection. This is A and B. So this is a formula. Write it down. It's an important formula. And we're going to see an example of it. Here's the example. In the fireman game, the spinner is spun. So, right, and okay, find the probability of getting a 3. I'm just looking around here. I think I can ignore the outer bits. There are 2 sections which have 3. Okay, so this is 2. How many sections are there? There are 6. Okay, 2 out of 6. Well, I can simplify that to a third. B, pick a probability of up the ladder. Up the ladder. Well, that says up to the window. So I assume, what's that say? It's carry to say. I think I'm referring to these yellow ones. I'm not really sure, but yeah, I think it's these yellow ones. Anyway, there's 3 of them. So it's 3 out of, how many are there in total? 1, 2, 3, I think there's 12. So that's a quarter. What's the probability of getting 3 or up the ladder? 3 or up the ladder. Now, the temptation, I suppose, is you've got 2 answers, you add them together. Actually, just notice here, look, this one kind of coincides with this one. It kind of overlaps. This one's fine, this one's fine, this one. But here, which parts of this would I be able to use? I could definitely get that one. This one, if it landed here, if the spinner turned around and it was in this bit, that'd be okay as well, because it's in the 3. So that bit there is yes. That bit there is no. That bit there is yes. I'm just trying to get each little section. That's a 2 and a green, so that's no good. That's a 2 and a red. No. That's a 3, so that's okay. That's a 3, that's okay. This one's a yellow, so that's okay. So 1, no. 2 in the green, no. And that one's here. So I'm just counting round from this one here. It's 1, 2, 3, 4, 5. There are 6 sections, which is 6 out of the 12, which is a half. And explain why this tells us the two events are not mutually exclusive. Well, I think it's because of this. If I was to add these two, a third plus a quarter, you may recall you make these into 12, so you can just type this into your calculator. You get 7/12, and that is not equal to the half I actually got. And it's because these are overlapping here. This section here is both 3 and yellow. And if you're not careful, you count it twice. So just be aware of that. A couple of questions then. Customers are at a restaurant are offered a choice of chips and lasagna, or both. So obviously we've got 16 people. That's what that says. We've got 16 people offered the choice. 6 chose lasagna. 5, it seems, chose both. 2 chose chips, and 3 said, nah, I don't like either. So find the probability of choosing lasagna. Well, 11 people chose lasagna. How many people was out of 16? Find the people who chose chips. Well, 7 people chose chips. Notice I'm having to add them together. 7 out of 16. Find the probability that people chose lasagna or chips. Notice that symbol meaning or. Well, 6, 11, 13 people chose one or the other, or both. Explain why this tells us the two events are not mutually exclusive. But it's the same idea. If I was to the probability of L and I add it to the probability of C, I don't get what I get. Look at that, I'd get 18/16. That's impossible. You can't get probability more than a whole one. It's not equal to the probability of L or C. And that's why. What have I written as an answer? That's exactly what I wrote. You can't get the same answer when you do these two things, so it can't be mutually exclusive. Sometimes you get what are called given probabilities, and well, this is the symbol for given. I'll come to that in a bit. So we've got these different types of drivers, male or female, and they can buy different types of car. Now, it's referring to fuel consumption, petrol consumption. So some cars, like a little, I don't know, C1 or something like this, use hardly any petrol, but if you had a Lamborghini, it would use a lot of petrol. So one person is selected at random. Find the probability that this person drives a low-rated car. I'm just looking at the table. I've got this many people driving low-rated cars. What's that? That is 35. Do I know it's out of 100? I was lucky. They told it. Otherwise, I'd have to add up all those numbers. So 35 out of 100, you presumably can simplify that to 7 out of 20. Probability, then, remember this symbol means and. It's got an N in it. Probability the driver is a female and they drive a low-rated car. Well, that's just these ones here. It's a much smaller number. It's 23 out of the 100. Okay, and this one says find the probability that it is a female. Okay, so it's female, and the critical word there is given that they drive a low-rated car. So basically, because it is given to us that they drive a low-rated car, I'm only now looking at these people. So it's out of 35. How many of them are female? 23 of them are. And that's my answer. 23 out of 35, got there eventually. So look out for this symbol, given. Given. It means you restrict the number of things you're looking at. And we've got a couple of questions here. I don't think I'm going to get through them all. So I'm probably going to pause it there and we'll do these two, I think it's 2 questions. We've got this question to do. Oh, it's just one question, which we'll do in class. Thank you very much.